All right, good morning. Thanks everyone for showing up so early in the morning. Thanks Tarun. And let me also start by thanking Dheeraj and all the other organizers for their kind invitation. So I'm going to switch gears here and start something that I have been working on for the last couple of years. And the topic essentially is how can you generate primordial black holes from inflation? And more importantly, once you have generated them, what do you do with them? Okay. So of course, it has been discussed a lot that PBH could be a very interesting and novel candidates for the dark matter in the universe, something that we are still trying to understand what it is. But more importantly, once you generate these PBH from inflation, essentially in the very early universe, they are associated with a variety of imprints, which I will discuss in some detail. And they could be, in terms of secondary stochastic gravitational waves from the very process of PBH formation. In addition, there could also be imprints in the Hawking evaporation of these primordial black holes. And if I have time, I'll also discuss some of our recent works on the memory burden effect, which is something which has caught the eye of the community. All right, so this talk is based on a bunch of papers, as I said, that I have been working on with my PhD students over the last couple of years. All right, so I won't go into too much detail of the outline, but the main points that I will try to discuss on is that, first of all, as I said that, PBH could be a novel candidate for the cold dark matter, and how can you possibly produce them in the very early universe. Then I will discuss a bunch of these varieties of observational imprints. Some of this was touched upon yesterday in the talks by Samuel and Richa on the induced secondary gravitational wave backgrounds. But more importantly, there are also a bunch of other associated imprints, more importantly in the CMB, in terms of the extra relativistic degrees of freedom from the PBH evaporation. So you'll find that in some scenario, there's a nice complementarity between the GW observations and the CMB imprints arising in the same framework of PBH formation. And then towards the end, I will conclude. So this is what we know, we are all aware of, so-called the Standard Model of Cosmology. It includes radiation, baryons, dark matter, and dark energy. And this, of course, an empirical model, a working model for understanding the universe, so-called the lambda CDM, statistically homogeneous and isotropic on very large scales. So we know a lot about this, but at the same time, we also don't know a lot about it, in the sense that we know that, dark matter and dark energy should be there to complete the working model. However, we do not know what they are. Okay, and of course, if you look at the dark matter, there's ample evidence for the existence of dark matter in the universe, arising from varieties of different observations, namely the galaxy rotation curves, the bullet cluster, and also the CMB precision measurements of the CMB acoustic peaks in the temperature power spectrum. So more importantly, these kind of observations indicate the presence of dark matter in a qualitative way, but measurements of CMB also gives it a quantitative attribute, in the sense that if you want to really fit the data in the CMB power spectrum, you can also figure out how much dark matter should be there in this Standard Model of Cosmology. So it's fair to say that we know that dark matter must exist, we just don't know what it is. So it's one of the biggest known unknowns in the universe. All right, so we want to figure out what dark matter could be, and of course, over the years, over a few decades, many of these possibilities have been explored, arising from both the fact that the dark matter could be a microscopic particle, which has to arise necessarily from the beyond standard model physics. However, dark matter could also be a macroscopic particle. Okay, nobody stops you from thinking about that. And among these possibilities, PBH turns out to be one of the interesting candidates, and I will elaborate upon why that is the case. So first of all, that you can produce them abundantly in the very early universe. For example, during inflation, they are non-baryonic, non-relativistic, and nearly collisionless. This is all what you want for dark matter to be. There is no new physics required per se. Whatever you require for inflation will work for producing PBH during inflation. Of course, as we know that PBH are produced on the smaller scales during inflation. So they also serve as a very complementary probe to probe the small scale dynamics during inflation. And CMB observations largely constrain the large scale dynamics. Okay, so these are also interesting to explore what happens beyond the 10e force of inflation, which CMB observations are sensitive to. And of course, they give rise to a larger variety of observational imprints. Using them, you can actually probe the formation processes and their properties. So this is the constraint plot, essentially the fraction of PBH in terms of dark matter as a function of PBH mass. And in addition to these various observations arising from Hawking evaporation, gravitational microlensing, femtolensing, and many other observations, it still turns out that there's a few orders of magnitude gap available in this parameter space where PBH could be entire dark matter. So the interest of the community is to explore scenarios where you can produce dark matter in possibly in this particular range, which also goes by the asteroid mass range. Okay, this is a busier plot of the same previous plot where we put in many more constraints. So this plot is taken from one of the reviews that I wrote recently with my LISA colleagues. And you find that this range, which I mentioned in the previous plot, still remains available where you want interesting models to produce dark matter. Keep in mind that in any model of inflation wherein you want to produce PBH on the smaller scales, you need to preserve respect the constraint of CMB on the very large scales. So an upshot of how you can understand PBH formation from inflation, you know that the large scales which correspond to CMB scales leave the horizon during the earliest moments. And as I said earlier, CMB can only probe the first 8 to 10 e-folds of inflation. And these scales, let's say in blue, are very well constrained from the CMB observations. However, you could have a non-trivial dynamics on the smaller scales which exit the horizon during inflation. And let's say if you have large overdensities, these scales which would leave later but re-enter early the horizon, if they have large overdensities, these large overdensities, the moment they re-enter the horizon would collapse and can possibly form primordial black holes. So this is the physics that you want, that you are interested in, that you want to capture. And you can see that there is a large separation between the large scales and the small scales. But as I said earlier, you still need to worry about the constraints that you already have from CMB on the very large scales. The same picture in a slightly different way that, of course, you can think of the PBH being produced over certain critical overdensities, and only when scales with large overdensities re-enter the horizon, you think of them collapsing and producing primordial black holes. Okay, so this is the part of the parameter space in terms of the curvature perturbation as a function of co-moving wave number that is very well constrained from CMB analysis observation. And the other corner over here, small scales, is what one is interested in constraining better using PBH and CMB distortions, for instance. So one of the simplest models that people have looked at a lot, including us, is the single field inflationary model. However, you think of potential not being a simple monomial potential, but more like a polynomial potential. Okay, this is just a sketch of some models that we looked at. And the idea is that the large scales are essentially leaving the horizon during the nearly flat part of the potential, so that you respect the nearly flat power spectrum and match the CMB constraints. However, when the field rolls down during this so-called the inflection point, saddle point part of the potential, the fluctuations here, which leave the horizon around this epoch, so-called the ultra-slow roll, are greatly enhanced. And when these modes re-enter the horizon, they end up producing primordial black holes. Okay, this is one of the examples that we looked at a couple of years ago, and this is a simple polynomial potential. And we wanted to ensure that the CMB constraints are respected. So you can see the construction of this potential ensures that even at the large field values, and the CMB scales are leaving the horizon, the potential is nearly quadratic. Okay, so this is almost at the verge of being consistent or being ruled out. And one of the predictions of this model was that the tensor to scalar ratio was 0.25. So perhaps you can already see that this model is almost at the verge of being ruled out. However, this gives a very interesting phenomenology in terms of PBH formation. So as I said, that the scales which leave the horizon around the ultra-slow roll phase are greatly enhanced, while the large scales still have a nearly scale invariant, nearly flat power spectra. And for different values of the model parameters, you find that the enhancement almost happen in the same way. So now you can take that and figure out what would be the mass fraction associated with each of these power spectra. So you employ your favorite collapse formalism, let's say Press-Schechter, and you work out the PBS mass fraction, and it turns out that for certain, so the color coding remains the same across the two plots, and you find that for certain values of the parameters, you can actually find the PBH being the entire dark matter in these allowed asteroid mass windows. All right? So now that you have produced PBH, what do you do with them? As I said already in the beginning, that you need to ask the question about what kind of associated imprints it can give rise to. And one of the very imminent and immediate imprint is that they also give rise to a secondary background of gravitational waves. And this works as follows. This was again something discussed yesterday in a few talks, that the second order scalar perturbations, I mean the source comprising of second order scalars, will actually give rise to a source term to the tensor mode equation, and as a result, in all these scenarios, you will end up producing a secondary background of gravitational waves. And this is an important probe, because keep in mind that you are producing PBH from large scalar fluctuations. And as a result, this source term being large will give rise to a largish background of these secondary gravitational waves, in addition to the primordial gravitational waves, which are generated from the vacuum fluctuations during inflation. Of course, this is all the typical way you calculate the omega GW, and this is what you are interested in, so I won't go into that. But this is the quantity you are interested in, and the question you want to ask is that how does this compare with the sensitivity of future experiments? So this is what you find. Each of the peak in the primordial power spectra or the mass fraction will give rise to a peak in the gravitational wave power spectrum, and this you are interested in to figure out which observatory futuristic is going to be sensitive to these kind of background. The peak structure is very interesting because you would have seen by now that I had talked about three peaks, the peaks in the power spectrum, the mass fraction, and now a peak in the gravitational waves. And it turns out that these three peaks are very interestingly connected to each other. Okay, you can always relate the co-moving wave number at which there is a peak in the power spectrum to the peak in the frequency of the stochastic GW to the mass fraction. And if you want to produce a peak in the LISA band, which is sensitive or most sensitive around the millihertz frequency band, you find that the PBH that you need to produce should be such and such mass range. All right, so I'll move on and I'll talk about a slightly different aspect of PBH. For instance, let's say these PBH are not massive enough that they cannot be dark matter, but they are still produced somehow. How can you possibly detect them? Okay, if you invoke the Hawking evaporation constraint, you would find out that, let's say, very ultra low mass PBH would be completely evaporated even by BBN. So how can you possibly go and figure out to constrain the imprints of these ultralight PBH, which are already evaporated by BBN? So as you know that, if you go in this mass range, let's say less than 10 power 9, 10 power 10 grams, there are no constraints whatsoever on the fraction of PBH. And this is what we wanted to look at, that how can you possibly constrain any imprint arising from these PBH, which otherwise remain unconstrained. Okay, so you can look at the Hawking evaporation signature, as I said, and of course it works slightly differently for the spinning and non-spinning primordial black holes. I won't go too much into that. So you can think of these, a distribution of these PBH, which are ultralight, okay, but they come to dominate at some point. Remember, the universe goes into the radiation dominated epoch after inflation, but because PBH having a non-zero energy density, it will come to dominate at some point before being completely evaporated. So in this picture, you would have something called the early matter-dominated phase between the radiation-dominated epoch. And this gives rise to a very non-trivial imprint in the GW background. So this PBH distribution also gives rise to something called the isocurvature fluctuations because of their distribution. If you think of the Poissonian distribution of these PBH, the interseparation distance between the two PBH will give rise to isocurvature fluctuations. The time when these PBH evaporate, these isocurvature will be converted to adiabatic fluctuations. So we can now think of in this situation, in addition to having this inflationary counterpart, You also have a contribution coming from these isocurvature converted adiabatic fluctuations. And this is something you need to take into account while computing the stochastic GW. Keep in mind that these two contributions are otherwise independent. There is no correlation between them. Remember, you have to compute the power spectrum corresponding to phi. So essentially, you will pick the contribution which would be 2-point function of this and 2-point function of this, but there won't be a cross term because the origin of these two terms is completely different. And you can already guess what you are going to get out of it. Okay, there's a contribution here, there's a contribution here, and this is going to give you a doubly peaked spectrum in the gravitational waves. Okay, a contribution arising from the inflationary counterpart and a contribution arising from the PBH isocurvature turned adiabatic fluctuations. So this is what we found in these scenarios, a very characteristic doubly peaked power spectrum of gravitational waves for all these different scenarios. And all these different scenarios which are essentially labeled by the mass and the fraction of these PBH. Keep in mind that all these different scenarios do correspond to the ultralight PBH, which do completely evaporate by BBN. And there's only a very slight dependency about the PBH spin, at least in terms of the gravitational waves. And of course, the Hawking evaporation also gives rise to imprints in the CMB in terms of the relativistic degrees of freedom. And you can constrain those imprint, for instance, for different emission components, you can find out their contribution to the delta N effective, and you can possibly constrain it using futuristic CMB observatory. So you can see that there's a nice complementarity in these scenarios where you can simultaneously constrain the imprints of these scenarios into GW as well as in CMB observations. Okay, in the interest of time, I will very quickly mention that you can also look at, these PBH, ultralight PBH, giving rise to the stochastic GW background, which was detected in the PT observations. And there were many scenarios which were explored already. So what we were interested in is that a peaked spectrum around the PTA scales and asking the question, how does this compare better with the reference model that has been used in the analysis of PTA observations, namely the SMBHB, the supermassive black hole binaries. And we found that this kind of a scenario where you essentially have a resonant generation of the gravitational wave background can explain the nanograv observations. And when you do a full Bayesian analysis, you find that this scenario, for instance, with the ultra low mass PBH, actually worked significantly better in terms of a Bayes factor as compared to the reference model, which is the SMBHB. So in the last 1 minute, I'll very quickly discuss some of the recent thoughts that PBH could also be associated, or any black hole in general, could also be associated with something called the memory burden effect. So it was postulated that the semi-classical description of the black hole evaporation does not continue for the entire lifetime, in the sense that the moment the PBH or any black hole starts evaporating, this self-similar process will not continue until the black hole disappears. Okay, this was thought about recently, and a bunch of papers by G. Advali and co. They put out a formalism that the quantum back reaction arising from the emission components is going to affect the evaporation and the lifetime of the black holes. As a result, this self-similar semi-classical description will not continue for the entire duration. Okay? As a result, it's going to affect any imprint that you are going to compute from those black holes. For instance, they already showed that due to this effect, the evaporation is going to slow down, and as a result, even the smaller mass PBH could be a candidate for the cold dark matter. What we looked at is, first of all, what are the imprints of the memory burden onto the characteristic secondary GW background, and whether you can mimic the imprints of memory burden with, let's say, non-trivial reheating epoch after the end of inflation. So this memory burden essentially is characterized into the mass loss rate. So one corresponds to the classical or semi-classical Hawking formalism, while beyond a certain mass, it is affected in terms of this particular exponent that it slows down. Okay, so in this sense, the effects of memory burden are essentially characterized by these two parameters, essentially Q and N. And you want to ask the question that what would be a characteristic imprint of the memory burden onto the doubly peaked GW background. So we explored that and we found that the effects are very similar in the sense that if you look at a history which is away from radiation, there are imprints onto the GW background, the W peak GW background. At the same time, if you also have a situation when you take into account the memory burden effect, in the sense that Q and N are non-zero, you also get significant effect. And the question we wanted to ask is that whether these two effects could be degenerate. Okay? And we found that for certain parameter space, you can make the secondary peak in the GW degenerate with a non-trivial reheating effect, but the first peak still remains non-degenerate. So the conclusion from this was that the effect of memory burden is degenerate with the non-trivial reheating history only at the level of the second peak, which arises at the higher frequency range. But if you can simultaneously detect both the peaks from futuristic GW background, you can still disentangle the effects of a non-trivial reheating history from the memory burden effect. And if you are interested, we wrote a review, as I said in the beginning. It's a very comprehensive, up-to-date review on PBH and the gravitational wave signature. This was published early this year in Living Reviews. And I'm going to stop here. Thank you very much.
Thank you, Rajiv. You can have, okay, I'm sorry, I started scanning from here. So, yes.
Hi, thanks for the nice talk. So you mentioned that the peaking frequency and wave number and mass are related to each other. I wanted to ask how sensitive is the peak in the mass of the primordial black hole? How sensitive is that to the formalism you use to compute the mass distribution of the primordial black holes?
So there are a few things that you take into account while writing this relation. First of all, that the mass fraction is monochromatic. Okay? In practice, this is not the case. This is just an assumption. Most often, you actually get a broader mass spectrum or a mass fraction. Okay? So this is one crucial assumption which is always thrown into arriving any of these relations. But this relation is not too sensitive on the formalism that you choose. Okay, there might be just a factor here and there, but let's say if you take the peaks formalism or the press sector, this will not change much.
Okay, Shubhadeep and Prakash.
Hi Rajiv, very nice talk. So two questions. One is on the supermassive black hole PTA side. So when you told about the improvement in the base factor in comparison to supermassive black holes, do you consider the black holes to be circular or do you consider it's the environmental effect? Because I presume the peak is what you actually go for.
Yes.
So I would say that if you really consider the astrophysical scenario where you expect to have a peak, then this peak position will be highly degenerate with the PPH PQC.
Absolutely.
And as a result, the base factor don't improve.
Yeah. So this is a simplistic sort of, way to
but this is the realistic, I would say, in the next, when you have a detection, 5 sigma and above, I think we should go for including non-circularity. It's very important because
if I remember
there's
correctly,
no black hole without accretion disk.
even in all these scenarios, the environmental effects have not been taken into account. Okay, even in the PTA papers.
Two different things.
No, we're talking about
Talking about astrophysical black holes.
No. So
He's talking
when
about
I have a gravitational wave background produced from supermassive black holes, right? So they are not going to have in an empty region. They're going to have accretion disk. As a result, they're going to lose some energy with interaction with the environment in comparison to gravitational wave. As a result, you see a peak in the stochastic background.
But that will just change your reference value for the base.
No, it will. I have two peaks now. One can be a cosmological peak, another can be a astrophysical peak, and I do not know. Here the base factor improves because in the nanohertz gravitational wave data, we see a peak. There's a dip below 8 nanohertz, and it falls like this. So I can fit a peak better than a straight line model. That's why I improve. Second point, maybe I have time, 12 minutes?
Yeah, that's okay.
About the press sector formalism. So this is one of, because there's a lot of non-Gaussianity by construction, maybe it's worth seeing, because press sector is within the Gaussian limit.
Yes.
Tail may be the
Yes, so
culprit.
I didn't bring upon that point. Of course, as we know that the PBH form from the tail of the distribution, and if you have even slight non-Gaussianities, because you integrate in any of the formalism from delta C to infinity, any slight non-Gaussianities are going to change. So this has been looked at. Yeah. This has been looked at, For us, we just work with the Gaussian.
Let's move on to Prakash.
Sorry, yeah, very nice talk. I have a very naive question. So, given that PBH are one of the candidates seed for the seed black hole in the early universe, so as a result, they are also seed for, say, for example, supermassive black hole that we form. So, given that JWST is finding high redshift galaxies and supermassive black holes probably, so can you use this information to constrain the PBH masses in the early universe?
In principle, yes. But again, in that setting, coming back to Shubhadeep's question, there's a lot of astrophysical uncertainties around that you need to carefully take into account. You cannot just take, let's say something here, let's say over here, okay, sorry, here, where is it? Here, okay, you cannot take something here and start thinking this is already a massive enough black hole which could serve as a seed for the supermassive black hole in the later universe. There's a lot of, astrophysics which goes into from that to that. But of course, this would still serve, given that our understanding in lambda CDM to form these supermassive black holes is still very limited, okay? This still serves as a very nice, novel framework to think of that.
Thank you.
Okay, one quick question from you.
Hi, thanks for the nice talk. I just have a very naive question. So in the power spectrum, you showed that the enhancements, they're kind of going down. They're, first of all, they're quite broad and going down toward smaller scales. But so why do you get so narrow mass spectrum for primordial black holes?
Because you are still integrating the power spectrum, okay? As I said, you invoke one of your collapse formalism, okay? So as I said that it's up to you whether you want to call this really a monochromatic or a broad enough mass spectra, okay? Typically in inflationary models, okay, when you try to get a PBH mass fraction from any enhancement in the peak, unless you take a delta function peak, which is people have worked with, which is not realistic. If you think of any realistic inflationary model, this is a very, very general feature because the point is that you don't very quickly go away from ultra slow roll. It takes a few e-folds, okay? And as a result, the scales which are enhanced, okay, they're not going to be just, focused on, let's say, very small range because there's a finite duration of the ultra slow roll, okay? And this is imprinted in here, as I said, this is really still not so monochromatic. Inflationary models do not predict a really monochromatic, okay? But this is a fair assumption that you can work with because, as I said, that you are going to compare this with the constraints which are also derived using a monochromatic mass fraction.